This is the first of two longer video lectures covering one-way analysis of variance, also known as a one-way ANOVA. In previous lessons, you learned how to compare the means of two independent groups using a two-independent means t-test. An ANOVA is used to compare the means of three or more independent groups. These are the learning objectives covered this week. Upon completion of this lesson, you should be able to explain why it is not appropriate to conduct multiple independent t-tests to compare the means of more than two independent groups. Use Minitab to perform a one-way ANOVA with Tukey's pairwise comparisons. Interpret the results of a one-way ANOVA. And interpret the results of Tukey's pairwise comparisons. In this video, we'll start with the first learning objective. I'll also give you an overview of a one-way ANOVA. In the second video, we'll use Minitab Express and interpret output. At the beginning of this lesson, students often ask, why not multiple independent t-tests? For example, if we had three groups, we could compare groups 1 and 2, 1 and 3, and 2 and 3. The problem is that we would need to do three different independent t-tests. If we use an alpha level of 0.05 for each test, the overall alpha level would be almost 0.15. What if we had four groups to compare? We'd have to compare 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. That's 6 independent t-tests. If we use an alpha level of 0.05 for each one, our overall alpha level will be well over 0.05. This means that there's a good chance of making a type 1 error. If we think back to type 1 and type 2 errors in alpha levels, if we use an alpha level of 0.05 and run 100 independent tests, even if there were no differences in the population, we would expect about 5 of those tests to be statistically significant due to type 1 errors. This is a major problem. To overcome this problem, we use a one-way ANOVA. A one-way ANOVA will look at all of the groups together to determine if there's a difference overall. It will hold the overall alpha level to 0.05, so we don't need to worry about alpha being larger due to running multiple simultaneous tests. For the rest of this video, I'm going to overview some of the main topics related to conducting a one-way ANOVA. I'll introduce you to the F distribution, which is used to approximate the sampling distribution in an ANOVA. We'll review the 5-step hypothesis testing procedure, which is basically the same procedure that we used in previous lessons. And I'll also talk about pairwise comparisons. Then, in the next video, I'll cover using Minitab Express and interpreting Minitab Express output. In a one-way ANOVA, the sampling distribution is approximated using an F distribution. Earlier in the course, you learned about the Z and T distributions. You computed Z-test statistics and T-test statistics, and then used the Z and T distributions to look up p-values. With a one-way ANOVA, we compute an F-test statistic, and then use the F distribution to look up the p-value. The F distribution is unique from the Z and T distributions in that it has two different degrees of freedom. Degrees of freedom between groups and degrees of freedom within groups. Degrees of freedom between groups is equal to k minus 1, where k is the number of groups that are being compared. Degrees of freedom within groups, which is also known as the degrees of freedom error, is equal to n minus k, where n is the total sample size, and k is still the number of groups being compared. You may also see these labeled as degrees of freedom numerator and degrees of freedom denominator. Let's look at an example. We're comparing four groups. Group A has a sample size of 20, Group B has a sample size of 25, Group C has a sample size of 25, and Group D has a sample size of 20. Degrees of freedom between groups is k minus 1, or the number of groups minus 1. 4 minus 1 equals 3. We have 3 degrees of freedom between groups. Degrees of freedom within groups is n minus k. So the total sample size minus the number of groups. The total sample size here is 20 plus 25 plus 25 plus 20. So we have a total sample size of 90 minus 4 groups gives us 86 degrees of freedom within groups. When we construct the F distribution in Minitab Express, it will call these the numerator and denominator degrees of freedom. Let's go to Minitab Express now to construct an F distribution with 3 and 86 degrees of freedom. I'm on a Mac, so I'll go to Statistics, Probability Distributions, Distribution Plot. If you're on a PC, it will just be Statistics, Distribution Plot. We'll construct a distribution plot of a single distribution. This is an F distribution with 3 and 86 degrees of freedom. This is our F distribution. If we were doing an ANOVA by hand, we would compute the F test statistic and map it on here. F tests are always right-tailed, so we'll always be finding the area to the right of our test statistic. For example, what if we had an F test statistic of 2 here? Let's find the area to the right of F equals 2. We'll construct another probability plot. This time we want to display a probability. We have an F distribution with 3 and 86 degrees of freedom. Our test statistic is what Minitab Express calls an X value. So we said our X value, or our test statistic, was 2, and we want the default right-tailed test. This is the p-value for this hypothetical scenario with 3 and 86 degrees of freedom and a test statistic of 2. The interpretation of the p-value is going to be the same here as it was for earlier lessons. Let's go back now and look at the hypotheses that we're testing with an ANOVA and the 5-step hypothesis testing procedure that we're going to be using. We're going to be using the same 5-step hypothesis testing procedure that we used in our other mean and proportions tests. Step 1, check assumptions and write hypotheses. Step 2, calculate the test statistic. This is going to be our F test statistic. Step 3, determine the p-value. Step 4, make your decision to reject or fail to reject the null hypothesis. And step 5, state a real-world conclusion. Steps 2 and 3 will be performed by Minitab Express. We'll see this in the next video. Steps 4 and 5 are the same as they were in previous lessons. Step 1, however, is going to be a little different. Let's look at the assumptions that we need to check and the hypotheses that are used for a one-way ANOVA. There are 3 assumptions. The first assumption is that the samples are independent. In other words, there are different individuals in each group and they are in no way matched or paired. The second assumption is that the response variable is normally distributed in each population. In practice, we don't have access to data from the populations, so we look at the sample distributions. The data in each group should be approximately normally distributed. The third assumption is that the population variances are all equal. Again, we don't have the population variances, so we're estimating them using sample data. As a general guideline, we compare the largest sample standard deviation to the smallest sample standard deviation. The largest should not be more than twice the smallest. In other words, if the ratio of the largest to smallest standard deviation is 2 or less, then we say that this assumption has been met. Once we have checked assumptions, we can move on to write hypotheses. The null hypothesis will always be that the population means are equal. We write this as mu sub 1 equals mu sub 2 equals all the way through mu sub k, because recall that we have k independent groups. So if we had 3 groups, the null hypothesis would be mu sub 1 equals mu sub 2 equals mu sub 3. The alternative hypothesis is that not all means are equal. There are a few different ways that we can write this. I like to say that not all mu sub dot are equal. Mu dot is the population mean for one of our groups. So this is like saying that the population means in all of the groups are not all equal. Your textbook writes the alternative as at least one mu sub I does not equal mu sub j. Mu sub I and mu sub j stand for two different population means. When you run a one-way ANOVA in Minitab Express, this is how it writes the hypotheses. The null hypothesis is the same as what we've just written, but in words instead of symbols. The alternative hypothesis is that at least one mean is different. Some of our Stat 200 instructors do not like the way that this is written because it can be misleading. The alternative is really that at least one pair of means is different. One group does not need to be different from all of the other groups. One group mean just needs to be different from at least one other group mean. After we check assumptions and write hypotheses, we go to Minitab Express to compute the test statistic and determine the p-value. The calculations behind a one-way ANOVA can be done by hand. Sometimes in intermediate or graduate level courses, students are required to do this. In this class, though, we'll be using Minitab Express because the calculations can be tedious and time-consuming. What we really want to focus on here are the overall concepts. Minitab Express will give you an ANOVA source table. We'll look at this more in the next video. While I don't want you to worry about computing all of the sums of squares, you should know how to compute the degrees of freedom. And if you're given the sums of squares and information needed to determine the degrees of freedom, you should be able to fill in the rest of this table. For example, MS is mean squared. This is a measure of variability. The mean squared is equal to the sum of squared divided by degrees of freedom. The F test statistic, then, is the mean squared between groups divided by mean squared within groups. The F test statistic is sometimes called the F ratio because it's the ratio of variation between groups over variation within groups. In addition to computing the F test statistic for you, Minitab Express will also compute the p-value for you. So then in steps 4 and 5, you just need to determine if you should reject or fail to reject the null hypothesis. If the p-value is greater than 0.05 and you fail to reject the null hypothesis, you conclude that there's not evidence that any of the population means are different. If the p-value is less than or equal to 0.05, then you reject the null hypothesis and conclude the population means are not all equal. But that does not tell you which means are not equal. An ANOVA is sometimes referred to as an omnibus test because it gives you overall results but does not tell you exactly where the differences are. If we want to know where the differences are, we need to do pairwise comparisons. These pairwise comparisons are sometimes known as post hoc tests because they're conducted after the one-way ANOVA. There are many different methods for making post hoc comparisons. We're only going to cover one method in this course. That's the Tukey method. This is not covered in your textbook, but it is covered in the online notes, and Minitab Express will compute this for you. The Tukey method makes all possible pairwise comparisons, but unlike doing multiple independent t-tests, the Tukey method takes into account the number of tests that are being performed. So if we were comparing 4 groups, it would take into account that 6 different tests were being run simultaneously. For each pairwise comparison, these are the hypotheses that are being tested. The null hypotheses are that the population means are equal. The alternative hypotheses are that the population means are not equal. We could write these hypotheses out for all of the possible pairs in a scenario, but in the next video, we'll see that Minitab Express will give us one table with all of the test statistics, p-values, and confidence intervals that we need. So typically we don't write out all of the possible pairwise tests, we just report the one table that summarizes all of them. This concludes part 1 of the one-way analysis of variance video lecture. In the next video, I'll show you how to use Minitab Express to conduct a one-way ANOVA and how to interpret its output.